Hello everyone, welcome to the Simulation Best Practices for Mixing Equipment webinar. My name is Jesus Ramirez and I am part of the technical team of Ocean Engineering. Today we are going to make a presentation about simulation of mixing equipments and show you how computational simulations can improve these equipments under operating conditions. In this presentation, we are going to talk about the challenges in the mixing industry, quantified impact of simulation on efficient use of mixing equipment, and also we will show some examples of how simulation is used in this field. We will divide this presentation into sections. First, we will talk about mixing equipments that involve fluids, and later, we will talk about solid powder mixing. Mixing is a common upstream process among different industries, let's say chemical, pharma, consumer products, food, among others. While the product is different, the objectives are similar, namely increasing the yield while ensuring the required mixing behavior and hence the final product quality. In the past, mixers seemed black boxes where processes were improved mostly by trial and error. However, the science and technology involved in the design, functionality, and application of the mixers indicate otherwise. Generally, some of the aspects to consider in the mixer design processes are the temperature, the need of aeration, the agitation level required, and the flow dynamics behavior. Due to the lack of adequate sensors, it is impossible to perform a complete characterization of the flow inside the mixing tanks. Also, the costs associated with experimentation in mixing tanks, particularly for big ones, make it unviable to develop trial and error processes. For this reason, computational fluid dynamics has been used in the last years for accelerating and improving the mixing tank designs. One of the engineering challenges in the mixing tank design is how to predict their performance for different products and operating conditions, as well as how to adapt these tanks for process changes. Again, the objective is to increase the yield. On the other hand, customers typically have different plans across different geographies, but they need to ensure product consistency. This is what scale up and scale down means. Let's say, how to ensure the same product is coming out from different plants having different tank sizes. Therefore, one of the most common questions that come to the process engineer's mind is how to scale up a benchtop tank into an industrial size one. The answer to this question is not straightforward or easy to get. To summarize, then we can say that a customer have a design goal that is doing an efficient and cost-effective mixing processes, of course, for bringing quality products to the market in less time. For that, the design requirements can be summarized as follows. For example, doing a scale-up of various units operation from the lab to the plant scale, adapt the system mix equipment to a new formulation or operating conditions, to ensure the efficient plant operations and meet the government regulations, and finally, ensure batch quality consistency through the digitalization. Then, basically, with this is that engineers, process engineers, works when they want to improve or to design mixing equipment. And for this, computational simulation is a very, very good tool to help to achieve this goal. Now, let's talk about how the simulation have helped some industries in improve their operations and improve their revenue when mixing tanks are used. One of the ANSYS customers developed an improved impeller for the mixing tank used in fiber manufacturing. The proposed design provides a 5 times better mixing for solid suspensions using 12% less power. Simulation helped the engineering team make design decisions that balance mixing performance and power draw. Another customer was able to decrease the time required for cell culture growth by 30%. This means several days of time savings. Details are presented in the webinar above. According to discussions with different pharma companies, the use of simulations allowed them to have an increase in their revenues of around 1%. This means millions of dollars of revenues per batch. You can see more information about this in the article mentioned above. Now, let's talk about some applications for mixing equipments that involve fluids. Commonly, in a first stage of analysis, the companies are interested in mixing tank characterizations having the following goals: potential scale-up issues to be identified for risk analysis, impact of geometry on the product quality, impact of operating conditions that affect the unit operation, and retrofit the new process in the existing equipment. For doing this, it is common that the first analysis is done using a single phase mixing system. Then, with that in mind, using CFD allows to completely characterize the flow behavior in both simple and complex geometry. It is also possible to determine the influence of the tank and impeller geometry over the fluid dynamic behavior inside the mixing tank. According to this, the most frequent properties and characteristics extracted from CFD simulation for mixing tanks are velocity fields, shear stress fields, recognition of recirculation zones, streamlines, and power consumption estimation. One application example is shown in Figure 1, where you can see two different impellers geometries. Therefore, among other applications, with CFD, it is possible to do virtual prototyping and analyze the effect of the impeller shape over the mixing tank performance. To summarize, a common first approach in the design process is to assess the mixing tank behavior using only a single phase. By doing this, there is a reduction of the required computational time for solving the model, which in consequence makes it easier to do parametric studies or design of experiments to get adequate operating conditions or for scaling purposes. As we previously mentioned, doing scale-up represents a significant challenge, both in time and money, for certain processes. By doing your own CFD analysis or by doing a consulting project with us, your company can achieve the necessary process understanding and accurate scale-up conditions for your mixing tanks to go from lab scale to plant scale. With CFD, it's possible to get valuable insights into the physics of scale-up and the risks involved. Basically, CFD simulation helps companies in decision-making on equipment sizing and cutting down on expensive raw material usage for the testing process. Therefore, CFD simulation can save hundreds of thousands of dollars, providing characterization that apply to the overall scalability process, reducing the need for building and testing prototypes. One straightforward way for doing scale-up using ANSYS CFD is by using the parametric analysis and the design of experiments. For example, in ANSYS applications, you can define key simulation properties to be parameters. Also, you can then manipulate the parameters at the project level in Workbench to investigate the design alternative. A set of parameter values representing one design alternative is called a design point. You can create a set of design points in tabular form and run them automatically to perform a what-if study. On the other hand, a design of experiment is a scientific way to reduce the number of experiments while still gathering enough data to understand the relationship. ANSYS, through the Design Explorer, proposed many design of experiment schemes to help engineers to achieve the best results. For example, here you can see how the velocity distribution inside a mixing tank changes depending on the tank scale. The same procedure can be done for different flow fields, and the changes can be correlated and shown in a response surface manner for making decisions, as is shown in this picture. Now, let's talk about another way of modeling the mixing tanks. Let's say application where gas and liquids are involved. It is common to observe that in many systems the mixing process occurs simultaneously during filling. This historically has been a challenging problem, and while it could have been accomplished, it used to take a long time to simulate with high fidelity. Recent advances in solver technology have reduced the turnaround time for this simulation by an order of magnitude. One of computational simulation's key features is to observe how the flow behaves inside the mixing tank. For example, We can watch how the mixture process evolves qualitatively and quantitatively in a mixing tank with an immersed mixing. We can check it here. Then if we check, we see how this will evolve inside the mixing tank when we are filling, we are injecting mass, and when we are using the immersed mixer. Also, you can see how the quantitative analysis is also linked to the qualitative analysis. Then we can visualize what's happening inside the mixer tank, but also we can check the numerical information that is also important for making decision. Then this is a good feature of ANSYS tools for engineers that works in this kind of application. Also, in this other video, we can check another application. For example, here we were interested in looking at the mixing and the free surface evolution as the mass was injected. In this part, we are interested on the board prediction for those cases where, for example, we want to check how is the turbulence behavior, how is the free surface behavior if you have a bubble formation, in those cases that bubble formation is not good for the process, then to recognize where are these bubbles formed and how they are distributed. Also, we can extract information about the shear stress for those cases where the shear stress is important. And if you can see, we can check that with using CFD and how the free surface, how the turbulence start to act over the fluid inside the tank, and also if we have this kind of bubble formations and flow behavior that we want to avoid, or just for having a knowledge or a deeper knowledge of what's happening inside the tank. Also, another application can be the prediction or the validation of the border depth when we have an stirring tank. Then, for example, in this case, we compare our simulation with experiments from Ciofalo et al. Basically, we use two different approaches. We use an steady state simulation and a transient simulation using the hybrid NITA. That is one of the last numerical approach that ANSYS has developed and that have given the engineers a faster solution for transient simulation. Then you can see here what is the comparison from the simulation results and the experiment results. They are pretty close, and this is a good news. Then we can see here how it looks like, and this is something that we can see using computational simulation. We can have an idea of how is the flow behavior inside the mixing tank, but also we can extract numerical data to compare with experimentation or with previous analysis to validate the model, or to generate new operating conditions or changes or new designs for improving the process. Another application for gas-liquid systems are the bioreactors, which are basically any manufactured device or system that supports a biologically active environment. One type of bioreactor are the air-lift bioreactors, which are reactors for large-scale aerobic cultures where gas is inserted via an air-lift pump. Another application for gas-liquid systems are bioreactors, which are basically any manufactured device or system that supports a biologically active environment. One type of bioreactor are the air-lift bioreactors, which are reactors for large-scale aerobic cultures where gas is inserted via an air-lift pump. These kind of systems have some operating problems that must be solved or avoided. For example, exotic strains of cell cultures grown in cutting-edge bioreactors, which result in therapies which easily can exceed $100,000 per gram of API. Ensuring sufficient respiration is critical to be sure that the goals are met. High yields means more life-saving therapies will produce per batch. The key to predicting the gas hold-up and the interfacial area are met with advanced ANSYS multiphase models. These models track the gas and liquid interaction, even predicting the bubble size and shape. This allows ANSYS to help your biology and process engineering specialists to predict with confidence the mass transfer dissolved oxygen, the carbon dioxide, and other gases. For example, let's talk about these pictures. And you can see how the oxygen or the gas is entered or injected into the mixing tank by the sparger. You can see how is the injection and how with the impellers the oxygen or the gas is distributed inside the tank. The idea is to have a good behavior of this distribution for having uh, improvement on the process. This can be easily done using CFD. Also, we can extract how is the normalized concentration at a desired point, let's say like a proof point, like is the equivalent like a sensor, then we can test how is the concentration on that point. In CFD, we can have multiple points, infinite number of points to track, and compare the data obtained from that point with experimental data for validation purposes and for starting like a virtual prototyping for a validated model. Also, we can see here how a trace agent is injected in a random part of the missing tank and how it is distributed and it becomes uniform and mixed with the solvent inside the missing tank. Then it is very easy to observe this using CFD and to have insights of what's happening with the gases and with the mixing processes we are interested on. Another application for mixing tanks is the analysis of solid suspension. In this case, the customer goal is different. For example, the customer wants to ensure that adequate solid suspension in the tank, also wants to analyze the dissolution or crystallization system, or to minimize the power requirements to have a longer impeller life and also a longer vessel life. For this, we have different solutions. For example, we can predict the flow patterns and turbulence in an accurate way. Also, ANSYS have advanced modeling uh, approaches for solid liquid mixing, along with reactions or different drug models that accurately predict the particle behavior. Also, as a big part of this, we can create a design of experiments to find the optimal operating conditions. With this, the customer receives some benefits. For example, it allows them to understand the missing characteristics as flow patterns, solid distribution, and cloud height. Also, they can predict the shear rate and shear history, and also they can minimize batch failures. We can see, for example, in the picture in the left bottom corner, how it is the effect of using one or two impellers on the cloud head height and the volume fraction of solid inside the mixing tank. Also, we can see that this behavior is very similar or close to experiments. Then that means that the solutions given by ANSYS are tested solutions and validated solutions for making decisions. Something important to remark is that understanding of solid suspension is key for many applications. For example, crystal growth, solid catalyzed reactors, dissolution studies, and situations where bits are hosting biological cells. A uniform solid distribution is favorable outcome, often increasing the speed may end up breaking crystals. At the same time, a minimum velocity, also called the just suspend speed, is required to be maintained. As you can see in the left bottom animation, you can observe how the cloud height prediction and visualization can be obtained from a CFD animation or a CFD simulation. On the other hand, The top right image are coming from a comprehensive analysis of a conical bottom reactor. In this case, water is used as liquid and solids are with 180 microns diameter in size. Reactor was subject to different agitation rates in this study. 3 rotational speeds were studied. You can see in the image that the solid distribution is compared for the three different rotational speeds. It was observed that the speed of 100 rpm and 150 rpm are not adequate to suspend the solids. For instance, the velocity of 220 rpm predicted that this speed was good enough for keeping the solids suspended in the flow. And you can see here how the solids tend to settle at the bottom of the reactor for the 100 and 150 rpm, and in this case, it seems that they are well suspended or well mixed inside the reactor. As you can see, using computational simulation can give you a detailed information of the flow field. For example, you can obtain the shear rate characteristics for checking if some of your solids will be damaged by exposure to regions with high shear. Also, you can predict just the suspension velocity, just to know if your solids will settle or not. Or also, you can predict the solid concentration profile throughout the vessel. Another type of mixer equipments are the static mixers. The static mixers are common in the process industry, let's say chemical, consumer products, food, among others. They have the advantage of being part of a continuous process rather than a batch discontinuous, which makes them attractive to high-yield processes. As always, the goal is to ensure proper mixes on the two or more ingredients. The challenge comes when the properties of these fluids are quite different. Static mixers impose a considerable pressure drop, and hence accurate system sizing is of remarkable importance since it will directly influence the operation. At the same time, they also impose significant shear onto the system, which may result in material degradation, depending on the application, of course. Different configurations of static mixer exist. For example, the SMX, that is the one that we are showing here, and the Kenix mixers are the most common. However, in recent years, there has been a development of new static mixers and new designs to improve the efficiency of mixing and also to reduce the pressure drop. For doing this, a virtual prototyping procedure using computational simulation is a good approach to prove concepts, to develop ideas, and to get the best result or the best design in a shorter time. In the pictures, you can see a typical SMX mixer. That is the one that is shown in the top right part of the slide. In the bottom part, you can see a contour that shows the concentration variation of a tracer that was fed from the side inlet. It is obvious that the operating conditions need to be adjusted to ensure complete mixing. And this is the kind of things that we can see and we can observe using CFD or computational simulations to get the proper behavior of the flow. Then in this case, it is obvious that the designers need to do changes in the geometry of the static mixers to get a good result for mixing. Then this is not working as we expected, as the designers expected. Then, but this is only possible to see in this level of detail by using computational simulations. Finally, another application for this kind of mixing equipments that work with fluids is clean in place. In this case, the customer goal is basically to have a sufficient and consistent cleaning of process. Of course, do a sizing of the systems across the different plants and to minimize and also predict the cleaning time material. For doing that, uh, We can do single and multi-phase simulations. Basically, we can predict the free surface behavior, the droplet formation, and also we can estimate what is the jet behavior and how is the liquid film formation inside the tank. With this kind of models, you can analyze the effect of the nozzle and the sprite, and to for new designs or for head selections, also to estimate the time for having a complete cleaning, how much liquid will you consume for doing this clean process, and which is the field coverage inside the tank with this kind of um, when you're cleaning. Then this kind of application, as you can see here in this video, is pretty interesting for for estimating operation times, or for the time that of that these tags will last in the process. And for example, if you want to stop the process, or you need to stop the process for cleaning the tanks, you can estimate how much time does it will take. And this is a pretty interesting application for this kind of computational modeling. Now let's talk about powder and solid mixing. Powder and solid mixing is achieved in the following ways: using a mechanical device that rotates, using a stationary vessel with agitators, using a vibration unit, using a gravity motionless device, and other ways that we are not going to discuss. Most mixers split and recombine the powders to create new interfaces and to remove segregation and stratification. However, these same devices also can induce segregation of powders based on difference in particle size, particle shape, or density. Therefore, understanding how this equipment works is of vital importance for engineers. Three types of particle motion are generally responsible for mixing of powders. Let's say convective mixing, shear mixing, and diffusive mixing. In the diffusive mixing, we have some equipments of the V-blenders, the double cone blenders, and the drums blenders. For the convective mixing, we have the ribbon blenders, the screw blenders, and the paddle mixers. Finally, for the shear mixing, we can find the rotating drum and the block shear mixer. These are equipments that are used to transfer many types of granular material from coarse grain to very fine powders. They are used in almost all industries where granular material needs to be transported. Since these equipment can be seen in a wide range of industries, it is common to see that they have many different types and shapes. However, they have the same main engineering objectives, that is, to ensure the material flow. Also, as the mixing equipment that involve fluids, their goal is to allow for reduction in operational costs and increase process reliability. We can model this kind of mixers using one of our newest tools, let's say Rocky-DEM. With Rocky-DEM, we can apply the discrete element method for modeling particles with real shapes occupying real volumes inside the model. And as you can see in these pictures, these particles can be spherical or can be with any shape that you need, that you want, with the properties of the material, real material particles, and with the motion that they will have inside the device. Then with this kind of solver that analyze the particles is focused on the particle behavior, we can determine if the mixing of powder and solids is good enough, or if we need to do changes on the designs or on the concept we are testing before moving to a manufacturing stage.